the algorithm of AIMNet2. And but AIMNet2's algorithm is mainly based on the message passing. So here on the right part, I'm showing you guys like the details about the message passing layers inside AIMNet2 model. So AIMNet2 has three message passing layers, and it mainly takes three um, inputs of a molecule that is R, Z, Q. So R is the coordinate of each atom inside the molecule, and Z is atomic numbers, and Q is the total charge of the molecule. For the initial layer of message passing, like the coordinates of each atom will be initialized into geometric descriptors, and we have a Gaussian-based symmetry functions to process this initialization, and atomic number will be directly initialized into atomic embedding through torch embedding setup. And these geometric descriptors and atomic embeddings will be combined through the convolution and concatenation to serve as the input, and we will be fed into a multi-layer perceptron. From this multi-layer perceptron, like the output from this multi-layer perceptron will be split into the delta A, delta Q, and also a weight factor. So delta A will be used to update atomic embedding for each atom, and delta Q and the weight factor will be passed into a formula called neural charge equilibration. Its NQE is right here, just below the scheme. And through the NQE, we can initialize the atomic partial charges for each atom. And this is a initial step of the message passing is also the first layer. And for the second layer, we do something really similar. But the only one thing that is different is that because we have atomic partial charges, and atomic partial charges will also be combined with the geometric descriptor. And this kind of combination will be concatenated together with the combination between geometric descriptors and atomic embedding. And finally, this more comprehensive input will be passed to the multi-layer perceptron. And we do the same thing. And in this case, we do not have to initialize atomic partial charges. Instead, we update atomic partial charges through the neural charge equilibration in the same way. And in the last layer, we do not do any updates. We repeat what we did for the second layer, and we do this kind of convolution and concatenation passing to a multi-layer perceptron. And the output between these two multi-layer perceptron we call AIM is atoms in molecules. It's kind of like a representation, like a vector representation of the whole molecule. And we just pass this representation to another independent multi-layer perceptron to get the output of the local energy of this molecule. And if you look back to the left, the local energy will be combined with the dispersion energy, which we directly take from like the D3 dispersion is there is available GitHub package to is the implementation in PyTorch. And also we have the electrostatic energy. This is calculated based on the atomic charges we updated during the message passing. And all these three parts, we just add them up, then we can have the total energy of a molecule. So this is a whole algorithm of AIMNet2. I also have a like a detailed like code interpretation document I will share later after this meeting in our channel, and also I will just upload it to the Notion notes. So after having a like a basic understanding of AIMNet2's algorithm, I will share the tutorial about how to train AIMNet2 and also how to use the compiled model to do some applications. So let me just share my Notion note. So here is a Notion note I shared later this morning. I think, yeah, this morning in the general channel. So for AIMNet2 tutorial, I split it into two parts. One is training session, the other one is usage. For training session, we currently have two GitHub repos. One is AIMNet2 Central, AIMNet Central. Another one is AIMNet2 and also the AIMNet2 interface repo. So I'm currently using the old one because we still have some small bugs need to be fixed for the AIMNet Central. So if you go to AIMNet you can just click on this link. You can see how to download the um, required packages for the training part. And also for AIMNet2, this one, you can find all the packages you need to do the interface with ASE and also Python ciphers. So here is what you have to do for the training session. First of all, you have to prepare a data set, and this is the structure. Sorry. And this is the structure we require for the training. It's a H5 file, and you have to prepare your charges, coordinates, energy, forces, and also numbers. Numbers are atomic numbers. So input are charge, coordinate, and atomic numbers. And for your prediction label, you have charges, energy, and forces. If you want to train so here I just put a note like if you want to train some open shell structures, you need another two keys. For the input, you have to add your multiply state for each molecule, and also you need to prepare the spin charges as the prediction label in your data set. For training, we also need, except for the dataset, we also need a training YAML file and also model YAML file and SAE file. I'll explain them one by one. So for training YAML file, where you just specify all the training parameters. So here is an example, like what you have to specify, like how you're gonna split the data into train and the validation, and also you have to specify your input and output labels. For data set, we also have different like sampling options. You can sample the data in atoms or in molecules. It's up to you, and you can specify the batches number per epoch. You can also design a loss function like the coefficient you assign to each loss, like force loss, energy loss, and charges loss. If you want to train on spin charges, you have to add spin charges here. An optimizer, scheduler, some really technical stuff. It's here quite in line with the like the PyTorch setup that you can refer to PyTorch GitHub to see what kind of like scheduler or optimizer you can implement here. And for monitoring the training process, we have the weight and bias logging logger here. So what you have to do is just like you need to prepare your own weight and bias account, and then you just have to log in first and provide your run name and project name. Then you can monitor the whole process on weight and bias website. And here is just the metric part. We use electron voltage based unit for all the training part and also interface part. So which means the energy will be like the final energy output will be in EV and forces will be EV per angstrom and so on. So that's about the training YAML file. And here we have the model YAML file. Technically, the model YAML file, you don't have to change a lot. And is only depending on you want to do some like structure exploration. So here we just specify all the structure parameters about the model and all the things like you have. This is actually for the validation part. You have dipole output and also quadrupole output, but these two things are not counted into the loss function in the train YAML file. But definitely you can just add them to your train YAML file as one of the metric for loss calculation. So one thing I want to mention is that for the model YAML file, because AIMNet2, when I presented the algorithm of AIMNet2, I mentioned that the dispersion energy is actually added back to the final calculation after the machine learning prediction. So here you can see we have two different model YAML file. One is just the one I just presented, and there is no dispersion term. But here we have the one with dispersion. So this is the dispersion part, and different DFTs has different dispersion, so we have to refer to the corresponding one to add it to this session. And the reason why we have two model YAML file is that during the training, we do not have any dispersion terms. So we will train the model using this model YAML file. And after training, when you do the compilation, when you try to convert your eager model into the GPT model, like the J compiled model, you have to use this model YAML file. Just keep all the above the same, only add the dispersion part, and then after the computation, the model will be able to predict the energy with dispersion included. So here we have all the files we need. We have our training dataset, we have train YAML file, we have two different model YAML file without dispersion, and I will show you how to start the training one by one. So uh, first of all, just you can execute this line to calculate the SAE file of the model. So SAE is self-atomic energy, which means it's like a baseline energy for each atom at a certain DFT reference. With this SAE file, deducted we subtract this energy from our training data set. So during the training part, we only train on the residues, and this kind of training scheme will be more accurate in practice. And after getting this SAE file, we can start the training. And the training, I'm providing a example file for the batch submission. And you can see here, you have the configure file. So configure file is basically your training, like hyperparameter control and how you're gonna like split the training validation data sets. And you specify your model file. That's the model YAML file. And remember, this model YAML file is without dispersion. During the training, there's no dispersion. And you load your data, load your SAE file, and you can specify the path you want to save your eager model. That's a PT, that's a PT file, and specify run name, project name. And these two parts are not really required because these are just, like you have to assign the names to your weight and bias website so you can just track your training process. And after training, as I mentioned, we have to compile our model from eager model, that's a PT file, to a JPT file. And in this process, we need to do two things. One is add this SAE deduction back. And another thing that is we have to add dispersion back. And what you have to do is you specify the PD file you saved from the training. And this is going to be the name you gave to your GPT model. And you just specify SAE and the model. And in this case, you will obtain a model like a model GPT. And this model GPT can be used in some interface stored in this repo. So now I will show some basic applications of using this GPT model to do some like predictions and also optimization. So, I'm sorry. First of all, given this model, we can do like single point prediction. So here is a Python code example. With this Python code example, as I said, for AIMNet2 model, you only have to prepare your coordinate, atomic numbers and charge. Here, I'm using the example, just assuming that you are dealing with open shell structure, so you also have to prepare a multiplicity of the molecule, and you just put them together into a dictionary and pass it to the model. You do not have to set the model to evaluation because during the compilation, the model is already at the evaluation status. And then you can make the prediction because force is not directly included in the prediction keys. So you also have to do this kind of manual autograde to get the force prediction. And this is about the single point prediction. We also offer geometry optimization, but the geometry optimization is interfaced with ASE. So from ASE, you can define the optimizing algorithm you want to use. And here we use LBFGS. And we have this kind of interfaces called AIMNet2 ASE. And this package is from the AIMNet2 calculator repo. And here I'm showing one function I use to make the geometry optimization. I added some actually unnecessary things like how to extract the result and also remove some unnecessary files for the cleaning. The only thing that I want to mention is I think the core part is here. Yeah. So AIMNet2 ASE, this calculator is exactly the same as other machine learning models interface with ASE. And you just have to call this calculator, provide your model path. This model path is going to be the GPT model you trained and obtained, and specify the charge and the multiply state of the molecule you want to do the geometry optimization. And then for the optimizers, this is exactly the same as ASE geometry optimization. You have to specify your um, optimizing, optimizing algorithm, and then you can do the geometry optimization. So here you can also extract your um, the energy of the optimized molecule. And uh, with this code, you can like for this is the example usage. Like what you have to do is just with this function, you just have to provide your model and provide your molecule. And usually I prefer to use like a XYZ file and the SDF file, and both of the files can be read by OpenBubble. It's another package you may have to download, and from OpenBubble you can directly read your the chart of the molecule, the multiplicity of the molecule, and also other basic things like atomic numbers and uh, the atomic coordinates for each atom. So this is about geometry optimization, and people doing reaction may be really interested in the transition state optimization and also the algorithm determination. So here we provide one example, interface with Python ciphers, and this documentation, this Python ciphers documentation is directly from their own repo, and they have different input files that we can follow. And the only thing different from the YAML file they provided on their GitHub is just the calculator part. So original Python Cypher's repo, they do not have the option for AIMNet, which means you can only specify your calculator type like XTB. You can also use Alka, which means you use DFT to do the transition state optimization. But here we have a AIMNet2 Python. This is the package we have, and with this package is actually a kind of like a extension of AIMNet2 model into their interface as one calculator that you can do the transition state optimization. And all the above are well documented in Python ciphers, like what kind of um, geometry type you can specify. And you can also do the pre-optimization. This is actually just pre-optimization of the molecules before starting the transition state search. And you can also specify different chain of state. And here I just use growing string. You can also switch it to NEB. And what you have to do is just have NEB here. And then the optimization threshold, they have Gaussian and also they have Gaussian loose, which is like a looser, it's not a tight threshold for the optimization. And then the transition state optimization, they have the algorithm RSI, I think they also have like a RSP RFO. This is just like the searching algorithm. And you can also do the IRC. So to just make sure your transition state connects both the reactant and the products. And this is also this I'm just showing this kind of input file is actually from the very beginning till the end, like we only have the reactant and the product geometries. You can do all of them with only one YAML file. And you can also, but if you have a like initial guess for the transition state, you can only start these two parts, which means the input, you just have to change it to your initial guess of your transition state, and you can start from transition state, which means you do not have to do all of them again. And this is um, the command if you want to run the transition state optimization using AIMNet. And it's worth mentioning that this command is also compatible with other calculator, which means if you want to compare um, like how AIMNet2 performs against maybe DFT, what you have to do, you just have to change the calculator to Alka if you have your Alka um, installed on your laptop or like cluster, and you can still run this one. You do not have to run PySys. You can still run AIMNet2 PySys, and this package is still compatible with Orca and other calculators like XTB. And here is just like what I talked about. Like if you have your structures ready for some other thing for if you don't want to run the whole transition state optimization, if you only want to um, run for example, if you do not want to run the IRC, you can also just run part of it, still okay. And in the end, I want to show you guys an example to calculate Hissing and also some thermodynamic properties prediction. So here is a Hissing calculation function I provided. And with this Hissing function, this is example from AIMNet2 calculator. And this calculator is different from ASE calculator. It's actually a calculator we developed ourselves. So Roman is a major developer of this package. And this package with this package, the input, I would say the input is quite the same as what we discussed before. Prepare coordinate, atomic numbers, charge, and the multiplicity. And you can see here, I just use the Pyball package from OpenBubble, and you can easily read all those information you need to prepare the input. And here is how you call this AIMNet2 calculator. Here I just specify I want to do Hissing, so I just set Hissing to be true and also forces to be true. And with that, you can directly pass your sorry, you can directly pass your data. Like this is the dictionary, pass this data into this calculator and get energy, forces, and Hessing really quickly. With Hessing calculated, we can do the thermodynamic calculation. And this thermodynamic calculation is interfaced with ASE again, because ASE has this vibration data package that you can easily calculate your thermodynamic properties. And for this function is definitely first of all you have to get Hissing, so it's kind of like you have to use it together with the Hissing function I just talked about. And here is the core part. After getting all the especially the Hissing part calculated, you can initialize your thermal calculator where you input your vibration energies. And this vibration energy is from ASE interface with the Hissing as the input. And you can also specify the geometry of the molecule. But here, if your molecule is like only two atoms, then it's going to be linear. You have to change it to linear. And also symmetry number, depending on the symmetry of the molecules. This is also something that you have to specify. And I do not find a really good package to read the symmetry of a molecule, so maybe you have to input this one manually. And then is just like the interpretation part. You can get your enthalpy and also you can get your entropy. And after getting these two things, because we have the temperature provided, we can get our Gibbs free energy. And this is only for one molecule. If you have your reactant and also your products, you can in this way calculate the delta G of the reaction. And so that's all thing I want to talk about AIMNet2's training and application. I have already shared this notion notes to I think it's a general channel. I will also upload as I promised before, like the algorithm interpretation of AIMNet2, some coding details stuff to help you guys understand how the AIMNet2's algorithm is developed. Thank you so much for your time. Thank you.